based on Monday's lecture, which you should have, maybe you've had time to watch it. It's not a big deal if you haven't. I looked at the potential due to continuous distributions of charge, like disks and rings. I did the disk, I didn't do a ring, but you know, and it's developed the same way we did with the electric field due to continuous charge distributions. You sum up all the little bits of charge over the object, and you get V is equal to K times the integral of dq over R. So that just means that you add up all the little bits of charge. The potential always goes like 1 over R, not 1 over R squared, and you get some expression for the potential. Once you've calculated the potential, the nice thing about potentials that I've mentioned several times is no vectors. So you don't have to do all that component stuff and looking at, you know, well, it's more involved, okay? Potential is a scalar, it's just a number, it has units of joules per coulomb, and for the disk, so here's a disk. Here you are at the center, here's the center of the disk of radius capital R, and, oops, okay, and you are at a point X above the center of the disk. I calculated an expression for the potential along this line X above the center, and it turned out to be V is equal to sigma 2 pi K. Sigma is that charge per unit area, so it has a uniform charge per unit area, sigma. Sigma was V was equal to sigma 2 pi K times the square root of R squared plus X squared minus X. And we talked about some limiting cases and so forth. Now, if you want to calculate the electric field, it's pretty darn simple. How did we generate this expression for potential? We integrate, by definition, you integrate the electric field. You do a line integral along the electric field and you get the change in potential. So going the other way, if you want to know the electric field based on some potential you calculate, it's the partial with respect to X, or the negative of the partial with respect to X times I hat, plus the negative of the partial of V with respect to Y, J hat, plus the negative of the partial of V with respect to Z, K hat. Okay? If you've never seen partial derivatives before, they're pretty darn simple in a very simple case. Okay? If you have a function of X, Y, and Z, right? I'm going to just write down some 3x squared y cubed z. Okay, let's just say that's our function. The partial derivative of f with respect to any one of the variables says, look at the rate of change of the function along the x-axis or the y-axis or the z-axis and hold everything else constant. So you're looking at the change of the function or the rate of change with respect to one variable, although it's a multivariable function. So the partial of f with respect to x, you take the derivative with respect to x and hold everything else constant. That would be 6x y cubed z. Okay? You get the picture? This is a very simple explanation of partials. They're a lot deeper than this, but for us right now, this is fine. Partial of f with respect to y would be equal to 9 x squared y squared z. Okay. Partial of f with respect to z is equal to 3x squared y cubed. Okay. Just act like everything else is a constant and take the derivative with respect to whatever variable I'm interested in. Okay. This says you can do that with the potential, and this is a vector quantity. And look at the change in v with respect to x times I hat, change in v with respect to y, j hat, and so forth. And that will produce the electric field. In practice, you're typically going to calculate for some distribution the potential. And then if you want to know the field, you do that. Okay. Based on that idea, since I have an expression for the potential with respect to the x variable. I don't know anything about y and z. We didn't calculate that. But I can calculate the electric field based on this. E is equal to minus the derivative with respect to x of that expression. Sigma 2 pi k, and I'll write it like this, square root of r squared plus x squared minus x. That's my bracket. Let's do that. So this is equal to negative sigma 2 pi k. Then I have to differentiate this with respect to x. That becomes x over the square root of r squared plus x squared minus 1. Okay. That's dead simple. I mean, that's simple. There's no y and z to worry about, but nevertheless, okay. Pull the negative inside. Oh, I need an I hat. It's a vector. Okay, missed. So let me change this around a little bit. I'll write it over here. So E is equal to sigma 2 pi k times 1 minus x over the square root of r squared plus x squared. And that is exactly I hat. That is exactly what we got when we did all that difficult integration and everything for the electric field. Okay, if you watch the video, you'll see that this derivation was much simpler. There's a couple of lines and no vectors to deal with. Okay. Any questions on this? I just think this is something you need to know. If we had had time in Physics 1 to talk about gravitational potential energy in terms of Newton's law of gravitation, it has a very similar form. You calculate the potential energy of a system, and then you differentiate it to get the force on a particle. Okay? In this case, you differentiate the potential to get the electric field. Fundamental theorem of calculus. What is it? Oh, give me part 1.
It's basically like, it says like when you take method of this variable, it changes the essential. I mean, I'm being pretty broad about it.
Yeah. Okay. Okay, what's part 2?
Part 2 is like, it's evaluating from the bound.
Yeah, all right. But isn't, the fundamental theorem is the integral is the inverse of the derivative, right?
Yeah.
Yeah, okay. That's all I was getting at. They're inverses of one another. We integrated to get the potential. You differentiate the potential to get back what we integrated, which was the electric field. Okay. All right, enough of that. I want to talk about energy, electrical potential energy. Remember, with the electric field, we had force was equal to QE. And we said, well, if you can calculate the electric field in some region, and you get an expression for the electric field at a point or in some region, you place a charge in that electric field, and that gives you the force on that charge. This is the same idea with potential. For potential, if you want to know the potential energy of a charge in a particular potential, it's just QV. The potential V does not depend on the charge that we're placing there. We're calculating this, typically, we're calculating this and we place some charge in that potential, and that gives you the potential energy of that charge with respect to infinity. 0 is out there at infinity, remember? Okay. You have to be careful with this. You have to pay attention to the signs. Okay. A negative charge in a positive potential gives you a negative potential energy. A negative charge in a negative potential has a positive potential energy. A positive, okay, you get all the combinations there, all right? Usually you're interested in the change in potential energy, delta U, right? We're looking at, how the potential energy changes. If it's a conservative system, then you can use that work energy theorem, change in kinetic energy, change in potential energy, and do calculations, which I'm going to do shortly. Okay. So we're going to look at some consequences of this idea. So let's say, like I had the other day, let's say you have a collection of charge. Okay, here's 3 charges. A 1 microcoulomb, this is a +1, a +2 microcoulomb, and a -3 microcoulomb. And they're at the corners of a square, and up here is some point. There's no charge at that point. I want to calculate the potential at that point quickly. Okay? Let's say this is 20 centimeters by 20 centimeters. All right. So I'll calculate the potential at that point. So V, I'll call it V star, is equal to K times 1 times 10 to the -6 coulombs divided by 0.2 meters plus, what's that one? 2 times 10 to the -6 coulombs divided by square root of 2 times 0.2 meters. Minus, because there's a negative here, minus 3 times 10 to the -6 coulombs divided by 0.2 meters, okay? If I did that right. That one's 20, that's square root of 2 times 20, that's 20, okay. So this is equal to K. So that becomes 5 times 10 to the negative 6 coulombs per meter plus, let's see, that's 7.07 times 10 to the negative 6 coulombs per meter, I think. And I'm going to write that as negative 15 times 10 to the negative 6 coulombs per meter. Add them up. Can't forget the negatives. That negative charge gives you a negative potential at this point. So this is equal to K times, that's 12.07. 2.93 maybe, with the negative times 10 to the negative 6 coulombs per meter. Some of you have your calculators. I hope you're checking me on this. Okay. So this is equal to 9 times 10 to the 9 Newton meters squared per coulomb squared times negative 2.93 times 10 to the negative 6 coulombs per meter. And that is equal to, can somebody calculate that? That's negative 2.6 something. Negative 2.6. There's another, give me another digit there. $2.64, maybe, times 10 to the 4. Is that right? Can somebody calculate that, please?
Yeah, that's right.
2.6, give me another digit there.
3.
3? Okay. Okay. That's the potential at that point. Just added it up. If I place a charge at that point, let's say I place a negative 5 microcoulomb charge at that point. The potential energy of that charge at that point with respect to infinity is QV. It's just Q times V. So U is equal to negative 5 times 10 to the negative 6 coulombs multiplied by V star, which we calculated here, negative 2.63 times 10 to the 4 volts. And that is equal to, what does that work out to be? Something positive times 10, 0.1 something. Somebody calculate that. 0.132 joules. A volt is a joule per coulomb. That's coulomb. That's the idea. If I know the potential at a point, place a charge at that point, can calculate the potential energy of that charge. Are there any questions on that? All right. So I'm going to use this idea and do something a little different. Look at the potential energy stored in a collection of charges. So here is this is a collection, I'll call it. Not a collection. I'll call it a group of charge. Okay. We're going to start out with one charge in the universe. Here's the charge. Q1. Okay. Then another charge magically appears out at the edge of the universe. Okay. And I bring that charge in. Let's say they're both positive, don't have to be. I bring that charge in from infinity and I place it right there. Well, if I brought that charge in from infinity and placed it there, I had to do some work. Okay? There's no losses. It's a conservative system. No friction, nothing heating up and losing energy or anything like that. So the work that I did to bring that charge in is stored in this collection of charges. There's only two of them, but okay. Let this distance be R12. Couple of ways to think about it. We could actually do the calculation. We could do the force through a distance, start at infinity and end at R12. I'm not going to do that. It's a fun calculation, but the result that you get is that the energy in the collection of two charges is simply equal to K Q1 Q2 over R12. Now, where did that come from? Well, there was a potential at this point which was K Q1 over R12. Placing that charge there gives you the energy, the potential energy. Okay. Now, I'm going to bring in a third charge. Put it down here. Q3. So here is R13, and this distance is R12. Damn. Not R1, I got R12. R23, okay. To put that charge at this position, I had to work against both of these charges. So the energy stored in this collection of charge is whatever I have stored up here, plus the energy that it takes to place the charge Q3 right here. So U, 1, 2, 3, that's for the three charges. I've got this amount of energy, K Q1, Q2 over R12 plus, I'm adding this one. So I've got some energy with respect to both of these. K Q1, Q3 over R13 plus K Q2, Q3 over R23. Yeah? Okay. We can keep doing this till the sun gobbles up the earth, but I'll do one more. Or I fall over, or you leave, or something. Okay. We can just keep building up this collection into. Let's do one more. I think you get the idea. I hope you get the idea now. So here's Q4. Here's R24. R34. And along this diagonal is R14. Okay? So to bring this charge in, it's the same logic. I had to do work against all three of these. So U, 1, 2, 3, 4. Well, I've got this. That's still stored in the system. I'm going to write it all out. K, Q1, Q2 over R12 plus K, Q1, Q3 over R3 plus K, Q2, Q3 over R23. But now I've got three more terms because I've added Q4, K, Q1, Q4 over R14 plus K, Q2, Q4 over R24 plus K, Q3, Q4 over R34. That's it. We can keep building, and I put one at the center. Okay, keep building up this group. That's the potential energy stored in this group of charge. Let's say that somebody comes along and interchanges 1 and 3. Or maybe they interchange 2 and 4. Or 1 and 4. Something like that. That may change the energy in the collection of charge. I don't think 1, 4 would change it. I think 1, 3 may change it. It could. Okay. That would change the energy in the collection of charge. You could look at the change in potential energy in this group of charges, or the energy stored in this group of charges, and calculate how much work you would have to do to make that change. Okay? So, I'm going to do a calculation similar to some of the stuff that we did in Physics 1. Recall that in a conservative system, delta KE plus delta U is equal to 0. That's the change in kinetic energy plus the change in potential energy is equal to 0. This says that if you raise the potential energy, you must lower the kinetic energy. If you lower the potential energy, you're raising the kinetic energy. It's this exchange between potential and kinetic. Think about the pendulum like a bowling ball. You're going from maximum potential energy, swings down, going to minimum potential energy, maximum kinetic, back up, maximum potential, minimum kinetic. It's this interchange between the potential and kinetic energy in a conservative field, the gravitational field. This is the same idea. If we have some potential energy stored in this collection of charge, and somehow we let the charges fly off to infinity or something, we can calculate this change in kinetic energy. They need mass though, right? Okay. Yeah, they need mass. So I'm going to do a calculation. Oh man, such a nice drawing. I've got to erase that. I'm going to do a calculation based on this. So let's say that I'm going to make it a little bit simpler than what I just had up there. Okay, so here are 4 charges. They all have charge Q and mass M. Q and M. Okay, so they're all equally charged, all the same sign and the same magnitude for the charge, and they all have the same mass. They're at the corners of a square. A square of side length S. All right. Are there some forces present? Sure, they're all the same charge and they're near one another, so they have this nice symmetric, we could prove this. Hopefully you can see it from symmetry. There's going to be a force on each one of these charges, sort of, along the diagonal. Force, force, and force. All these equal forces, something, they're bound right now, okay? But the electrical force is like this, Coulomb force. Somebody says, release the charges. So the charges get released. What's going to happen? Not a hard question. They're the only 4 charges in the universe. Yeah, they start flying off. All right? Is that force linear? Is that force decreasing linearly? No, because that Coulomb force goes like 1 over the distance squared. Okay? Here's the question. We're going to release the charges, and I've got a really fast camera, and at the instant that the square doubles in size, meaning s becomes 2s, I want to calculate the velocity of the charges. Seems like a difficult problem, but this makes it pretty simple because they're out here. Okay. All right. So now they've had time to move to a point where they are separated by a distance 2s. Because of the symmetry, and I'm not drawing it perfectly by any means, but now the square has side length 2s, 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 2s. Okay. And the charges have some velocity v. I'm not worried about direction, I'm looking at magnitude of the velocity. Okay. So we're going to use this work energy theorem, or sometimes they call it potential energy, kinetic energy theorem, whatever, to calculate the velocity. So KE initial is equal to 0, right? I said they start from rest. KE final, this might be a little bit tricky. What's the final kinetic energy of the system, of the group? Well, I'm saying at this distance 2s, they're traveling velocity v. I could have called it v final, but I'm calling it v. What was kinetic energy from physics 1? What was the equation or formula for kinetic energy? 1/2 mv squared, right? So each particle has kinetic energy 1/2 mv squared. There are 4 of them. So the kinetic energy, the final kinetic energy is 4 times 1/2 mv squared, which is equal to 2 mv squared. Okay? Initial potential energy. Keep wanting to write PE. U initial. It's this, right? That's the energy stored in this collection of charge. So I'm going to write it out in terms of these variables. So you get, okay, q squared over s plus k q squared over s plus k q squared over square root of 2s. That's these first three. And then when I added this charge, I got 2 terms, and then, yeah. So you get a plus k q squared over s plus k q squared over s plus k q squared over square root of 2s. Okay. All I'm doing is replacing these numbers with my variables over here. That's the potential energy of that collection of charge, the initial potential energy. I'm going to clean this up a little bit, get rid of this. So I've got four of these. 1, 2, 3, 4. Okay. 4k q squared over s plus 2k q squared over square root of 2s, right? That's U initial. I'm going to leave it like that. U final. Well, I'm looking at this point when S becomes 2S. So wherever I see an S here, I'm just going to replace it with a 2S. That will work, right? S now becomes 2S. It's still a square. Yes. Jenna says yes. We're going with it. All right. So we have 2k q squared over S plus kq squared over square root of 2s. Okay? Now, I'm ready to do the calculation based on this. Because I'm going to go ahead and get rid of this. I know that KE final minus KE initial is equal to U initial minus U final. That's delta KE is the negative of delta PE, or delta U. I always say PE, but I think in Survey they use, most people use U, so. In this life, no, in the text, okay. All right, so I'll do that calculation. KE final, 2mv squared. KE initial, 0. U initial is this thing. This is U final, so we need to subtract U final from U initial, and that gives you 2kq squared over S plus kq squared over square root of 2s. Okay. Solve for V. I don't know. Leave that as an exercise for the student. Find the common denominator. All right, I'll go through some of the pain. Let's see. 1 over the square root of 2 is square root of 2 over 2. So that gives you a 4 plus the square root of 2 times q squared over 2s. And that is 2mv squared. So v squared is equal to 4 plus the square root of 2. Oh, shoot. I left it. Oh, whew, that scared me. There's a k in there. Okay. Q squared divided by 4 ms. Then you take the square root. V is equal to, okay, 4 plus the square root of 2 q squared over 4 ms. And, okay, that's the best I can do. I think I got it right. I don't know. Check me on that, but maybe you can clean it up a little bit. Yeah, it's pretty ugly. Try it with the charge on the electron and the mass of the electron. Give it some distance, see what kind of velocity you get. Pretty fast. Okay. Are there any questions on this conceptually? Not so much the calculation, but yeah. Change in potential energy is equal to the negative of the change in kinetic energy, or change in kinetic energy is equal to the negative of the change in potential energy in a conservative system, meaning no losses, friction, no nothing. Works the same way with electric potential energy as it did with gravitational. All right, I'll see you again.